Today we're going to learn about the basics of number theory. So you might be asking yourself, what is number theory? In math, number theory is the study of the properties of integers. So let's review some important definitions. Counting numbers are the set 1, 2, 3, etc. They're the numbers we use for counting. So definition makes sense. The brackets being the set including. This fancy n is the symbol often used for the set of counting numbers. Whole numbers, you see, are the counting numbers plus the element 0. Mathematicians use n sub 0 or z plus as the symbol for this set. Finally, integers include negative numbers as well. Typically, the fancy letter Z here is used for this set. So these are just definitions. A prime number, also sometimes shortened as a prime, is a counting number with exactly two different factors, namely the number itself and the number 1. The first 10 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Note that 2 is the only even prime. I'd actually recommend you actually look at the list of integers between 1 and 100 and figure out which ones are prime. It's good practice. Those will come up again and again in contests. A composite number is a counting number that has at least 3 different factors. The number 1 is neither prime nor composite since it has exactly one factor, 1. So as a result, all counting numbers are split into 3 groups: prime numbers, composite numbers, and the group that only has the number 1. The expression prime factorization, it means taking any counting number and breaking it down into a product of only prime numbers. Any counting numbers may be expressed as the product of prime numbers. The existence and uniqueness of this is proven by the fundamental theorem of arithmetic. We won't prove that today, but it is a very important theorem in number theory. The process of representing a number as the product of prime numbers is called prime factorization. Let's look at an example. Factor 5720, 5,720. So it's very easy to apply the divisibility rules for 2, 3, 5, 9, 11, etc. So let's apply them. Well, we see it's divisible by 2 because it's even. We see it's still divisible by 2. Still divisible by 2. Now we see it ends in a 5. So we're going to see it's divisible by 5 down there. Okay, it's no longer divisible by 2. It's not divisible by 3 since the digits don't add up to a multiple of 3. But it does end in 5, so that was the obvious choice. We see if we divide by 5, it's now 143. Some of you may instantly recognize this as a 11 times 13. If you wanted to check for divisibility by 11, you do the alternating sum rule. 1 plus 3 is 4. You subtract 4, you get 0. If it's 0 or a factor of 11, it's divisible by 11. Since it's divisible by 11, we divide by 11, we get 13. 13 is prime, so we've completed the prime factorization. We had 3 factors of 2, a factor of 5, a factor of 11, a factor of 13, and we write this as 2 to the 3rd power times 5 times 11 times 13. So what's a good way to organize this? So we often check just the last digit. Is it even or 5? Then we know it's divisible by 2 or divisible by 5. We can also check the sum and alternating sum rules to see if it's divisible by 3, 9, or 11. And then once you've gone through the easy divisibility rules, you will look at successive primes. Typically start with the smallest one, 7, then 13, 17, etc. The last prime you've been attempting to divide by being squared is if the last prime you've been attempting to divide by being squared is bigger than your number is prime. That means you don't need to try primes bigger than 7 for numbers less than 100, since the next prime, 11 times 11, is greater than 100. So you might want to organize your calculation like this. Start with 5720, divide by 2, divide by 2, divide by 2, divide by 5, divide by 11, divide by 13, we get to 1. Okay, let's talk about the greatest common divisor, sometimes referred to as the greatest common factor. So we have a photo here of a math Olympiad coach. Maybe he had another job as well, and his math team. Now, Coach Barak wants to set up a team attack at practice, but he doesn't know how many students are going to attend. It might be 24, it might be 30. What is the greatest number of teams he can arrange so that each team is guaranteed to have an an even number of participants? So the same number of participants on each team. He knows for sure there'll be 24 students. He could arrange them into teams of 1, 2, 3, 4, 6, 8, 12, or 24 student teams. If there are 30 students, he could break them up into 1, 2, 3, 5, 6, 10, 15, or 30 student teams. The greatest number present on both lists is 6. So Coach Barak should arrange 6 teams. That way, whether he has 24 students or 30 students, 6 will evenly divide both of those numbers. The number we just found is called the greatest common divisor, GCD, of 2 counting numbers. It's the largest counting number that divides each of 2 given numbers evenly, in other words, divides them without a remainder. The GCD of 2 numbers is often denoted as GCD of A and B, where A and B are the 2 numbers, or if you know you're talking about GCD, you could even write it as A comma B in parentheses. You've already encountered greatest common divisors in elementary school when reducing common fractions. In the name greatest common divisor, the adjective greatest may be replaced by highest, and the word divisor may be replaced by factor. So other names include greatest common factor. Historically, other names for the same concept have included greatest common measure. That's somewhat archaic, and you're not going to encounter that in modern books or problems. So now that we know what the greatest common divisor is, how are we going to find it? To find the greatest common divisor of 2 numbers, it's often helpful to perform a prime factorization of the numbers. The GCD is the product of all the shared prime factors of the numbers. So let's look at this example. What is GCD, the GCD of 144 and 900? Well, 144's prime factorization is 2 to the 4th times 3 squared. The prime factorization of 900 is 2 squared times 3 squared times 5 squared. From their prime factorizations, we see that the 2 numbers share the 2 factors of 2 and 2 factors of the omitted 3. We meant to have 3 there. Look up here. We see both of them had 3 squared. If the GCD of 2 numbers is 1, we say the numbers are relatively prime or coprime. For example, neither 35 or 12 is a prime number, but they are coprime. Sometimes the prime factorization itself can be tricky. You know, in the middle school math Olympiads, 99% of the time, by using prime factorizations, you'll be able to find the GCD. But just for completeness, and because it's going to be important in your later mathematical education, I want you to be aware of the Euclidean algorithm. It's based on the fact that if the number A is greater than B, it can be proven that the greatest common divisor of A and B is equal to the greatest common divisor of the remainder of A when it's divided by B and B. So basically, I said the remainder of A when it's divided by B because when you do your long division, you multiply B by some integer and you subtract that from A and you're left with the remainder. And then you have B. So let's look at an example. What is the GCD of 833 and 221? Well, the prime factorization, I intentionally picked two numbers that wasn't trivial. That's a mathematician's way of saying it's kind of hard. So let's do the long division. We divide 833 by 221. We see the remainder is 170. So using this Euclidean algorithm, the GCD of 833 and 221 is equal to the GCD of 221 and 170. That's still not obvious. So we just repeat the process. We divide 221 by 170, we get a remainder of 51. Okay? We divide 170 by 51, we get a remainder of 17. If we divide 51 by 17, we don't get a remainder. So we're done. So the GCD of 51 and 17 is equal to 17. And just taking the chain backwards and just applying this theorem, it tells us that the GCD of 833 and 221 was the prime number 17. The partner in crime of the GCD is the least common multiple. So let's look at an example. Alice has invited friends to a party and she wants to buy cookies for everyone. She knows there will be 24 or 30 guests. So she wants everybody to get an equal number of cookies. What is the minimum number of cookies she should buy? To split the cookies equally between 24 friends, she can buy 24, 48, 72, 96, 120, 144, and so on. To split the cookies equally between 30 friends, she could buy 30, 60, 90, 120, 150, etc. So looking at those two lists, the smallest number of cookies she should buy to guarantee that she can evenly split them between 24 or 30 guests is 120. The least common multiple, LCM, of two common numbers is the smallest counting number that each of the given numbers divides evenly. So we often denote this as the LCM of A and B, or maybe the square bracket A and B. To find the LCM of two numbers, typically we perform the prime factorization of the numbers. The LCM of the two numbers is the product of all of the primes in their maximal power in the factorization of each number. So what does that mean? Let's look at an example. Going back to 144 and 900, what is their LCM? Well, 144 equals 2 to the 4th times 3 squared. 900 equals 2 squared, 3 squared, 5 squared. The biggest 2 is 2 to the 4th. Both have 3 squared, so the biggest 3 is 3 squared. The biggest 5 is 5 squared. There are no other primes. So looking at the maximum power of a prime that appears in any of them and multiplying those primes together, we see the LCM of 144 and 900 is 2 to the 4th, 3 squared, 5 squared, which equals 3,600. Okay. Curious minds probably noted that 144 times 900 equals 36 times 3,600, which equals 129,600. Indeed, if I multiply A times B, right, that's what I did, 144 and 900, it's equal to the GCD, 36, times the LCM, 3,600. This is always true. And you can easily prove that by looking at the algorithms we use from the prime factorization. And to prove how easy it is, That's one of the challenge problems for you this week. So I think this is a very fundamental property to know. The product of two numbers is equal to the product of their greatest common divisors times their least common multiple. Okay, now we're going to learn about the Chicken McNuggets theorem. Now, the mathematician who proved this did not call it the Chicken McNuggets theorem. Middle school math contests often call it this because middle school students typically like Chicken McNuggets, and when they first were introduced, they came in boxes of 9 and 20, which was a great example of this theorem. So, suppose, going back to this example, McNuggets came in boxes of 9 or 20. What was the largest number of McNuggets that was not expressible as the sum of integer numbers, multiples of 9 and 20? So in other words, what number, once I was greater than or equal to that, I just knew that I could take some number of boxes of 9 and some number of boxes of 20 and always achieve that number of McNuggets. That's going to be hard to do in our head. So let's look at a simpler version of the problem. What is the largest integer that cannot be expressed as the sum of integer multiples of 3 and 5? Okay, counting upwards, we know the solution is the largest integer before we first find 3 integers in a row that can be expressed as the sum of multiples of 3 and 5. Because once we've done that, we simply can add a multiple of 3 to those 3 numbers, and then 2 multiples of 3 to those 2 numbers, and so on to infinity, and obviously get any number larger than that. So 6 is 2 times 3. We cannot express 7 as combinations of integer multiples of 3 and 5. 8 is 3 plus 5. 9 is 3 times 3, no 5s. 10 is 2 times 5, no 3s. Okay, but now we found 3 in a row. 11, I just add 3 to 8. 12, I just add 3 to 9. 13, I just add 3 to 10, right? 14, I just add 2 3s to 8. So 7 is clearly the answer. For 9 and 20, a lot of counting or a little computer coding will tell you the answer is 151. But suppose you don't have access to a computer in this math contest, and we don't feel like wasting all of our precious time counting. Well, there's a theorem. For 2 coprime integers, m and n, let L of curly bracket m and n be the largest integer that cannot be expressed as the sum of the integer multiples m and n. L of m and n is equal to their product minus m minus n. So it's important that the 2 numbers be coprime to use this theorem. In other words, their GCD is 1. So 9 and 20 are coprime. The L, the largest integer that cannot be expressed as an integer multiples of 9 and 20 using this theorem is 9 times 20 minus 9 minus 20, 151. Using the example of 3 and 5, which are also coprime, 3 times 5 minus 3 minus 5 equals 7. So, haven't proven this to you. If you're curious, you can look up a proof online. But trust me, this works, and every once in a while, knowing this theorem will come in handy on a contest problem. But it's often easier to just remember how, we got there. If we take the smallest of the numbers, once we find 3 in a row, or if the smallest number in this case was 9, once we found 9 in a row that could be expressed as integer multiples, then we know we're done, and we found the largest number that cannot be expressed as the sum of integer multiples of m and n. Okay, the exercise is pretty straightforward this week. What is the only whole number that is not included in the set of counting numbers? Give you some prime factorization practice, 144, 2021. They love the current year in contests, and this is a tricky one. You might want to use the Euclidean algorithm for this one. What is the GCD of 5040 and 6125? what is the LCM of 484 and 330? I want you to practice these and get comfortable doing them, because as we get into more complex number theory problems later on this year, you need to know the fundamentals. And the fundamentals are prime factorizations, GCD, and LCM. Here's a word problem that actually you'll see is really an example of an LCM. Larry goes shopping every 3 days, Mo goes shopping every 4 days, and Curly goes shopping every 5 days. If these stooges all go shopping together on a Sunday, what is the first day of the week they could go shopping together again? 7. In a video game, red aliens are worth 7 points and blue aliens are worth 9 points. What is the highest score that can't be obtained by capturing only red or blue aliens? And 8, what are the GCD and LCM of 1183 and 3458? Again, the Euclidean algorithm may be useful here, or you could try a lot of long division. And finally, on to this week's challenge problem. What is the largest integer that can't be expressed as the sum of integer multiples of 5, 7, and 8? So you can't use the Chicken McNuggets theorem here. You have to use some logic and understanding how we find that. I don't know why these all defaulted to 1. So this is number 2. I'll fix that. Find the smallest positive integer, which when divided by 12 leaves a remainder of 11. When divided by 11 leaves a remainder of 10. When divided by 10 leaves a remainder of 9, etc. Down to when divided by 2, it leaves a remainder of 1. The third problem 1, also known as problem 3, find the smallest positive integer greater than 1, which yields a remainder of 1 when divided by any single-digit positive integer greater than 1. And the fourth problem 1, also known as 4, as I warned you, prove that the GCD of A and B times the LCM of A and B equals the product of A and B. Again, go back to how the prime factorizations of A and B are used to find the GCD and the LCM, and this is fairly straightforward to prove. Okay, that's it for this lesson. The next lesson will go into a little bit more advanced number theory work, and we'll meet again then.